Energy is released around us every minute of every day. We can measure that energy output in many different ways. For instance, one way is by measuring the amount of work that is completed in a period of time, by horsepower, pounds of thrust, tons of explosives. Astronomers could measure the energy output of stars in watts, but the numbers quickly become so large they would be incomprehensible. The sun, for example, puts out an incredible 10 to the 26 watts of power, trillions of times the total energy needs of our entire planet. Astronomers use the energy output of our sun as a standard unit for the energy output of all astronomical objects. This unit is referred to as a solar luminosity. The sun, of course, has one solar luminosity, while a particularly hot and massive star might have as much as 10 million solar luminosities. The Milky Way galaxy, comprised of hundreds of billions of stars, has a luminosity of 10 billion suns. And yet this energy output is minuscule compared to that of some exotic galaxies in the universe.
When you look at a spiral galaxy like Andromeda Galaxy or our own Milky Way, the disk of the galaxy and the core of the galaxy are roughly the same brightness. When you take a picture of these things, you can see both at the same time. But it turns out there's a kind of galaxy where it's much more difficult to see that. The nucleus of the galaxy, the very center of the galaxy, is much, much brighter than average. When you take a picture of these galaxies, the nucleus can actually totally overwhelm the rest of the galaxy. And what you're really seeing is that most of the energy of this galaxy seems to be coming from a very small region in the center. These are called active galaxies. We see quite a few of these, and the more you study them, the weirder they get. The spectra are different. You can see that what's going on in the center is different than what's going on in the center of normal galaxies. They're putting out a lot more high-energy radiation. You might see some ultraviolet and some X-rays from the center of the Milky Way, for example. But when you look at one of these active galaxies and you look at the center, you're seeing tons of ultraviolet, tons of X-rays. From some of them, you even see gamma rays, the highest energy form of light, that you really don't see very much of at all coming from normal galaxies. So obviously there is some different physical process going on in the centers of these galaxies.
Astronomers refer to these huge energy sources as active galactic nuclei, or AGN.
So an active galactic nucleus basically is the central region of a galaxy, and it's really defined as being a very bright center, a very active center. There's a lot of energy coming out of this very compact region in the center of the galaxy.
Recent advances in telescopes and detectors that operate in multiple wavelengths have refined astronomers' understanding of these AGN. But astronomers of the early and mid-1900s did not have the advantages that modern instrumentation provides, and were faced with a puzzle that involved several seemingly unrelated and bizarre objects.
In the early 40s, Carl Seifert, working at Mount Wilson Observatory, discovered that some galaxies had very bright centers, and that these centers showed interesting spectral signatures. They showed very strong emission lines, and sometimes very broad emission lines, which aren't seen in other galaxies.
A spectrum from a normal galaxy will be a composite of the spectra of all of the stars within it. That is, a continuous spectrum with dark absorption lines. Seifert galaxies display these normal absorption lines, but also show broad emission lines coming from the galaxy's cores. Emission lines in a spectrum indicate the presence of hot, low-density gas. The fact that the lines are broad indicates the gas is in rapid rotation. Gas that is moving toward us during the course of this rotation emits lines that we see as blue-shifted, while the gas that is moving away from us gives rise to red-shifted lines. This red and blue shifting of the gas blurs the spectral lines together, broadening them.
From atoms that we know, okay, very specific wavelengths, we can say, that wavelength there, that belongs to hydrogen. Or, that wavelength there, that belongs to oxygen. Oh, but wait a minute, it's really Doppler shifted, so it's moving really fast. We also can see how broad, how fast the motion is from the broadness of the lines. The Doppler shifting, both blue and red, on one line tells us that we've got material moving around.
Seifert's observations showed that the ionized gas in the nuclei of these galaxies was moving at speeds 30 times greater than those observed in normal galaxies. Astronomers divided these odd galaxies into two types. Type 1 Seifert galaxy spectra had narrow emission line features on top of very broad emission lines. Type 2 Seifert galaxy spectra just showed the narrow lines. Clearly, both types of Seifert galaxies had a big energy source in their cores to be able to excite the gas. But what this source would be was a mystery. Then, more pieces of the puzzle were found.
In the 1950s, radio astronomers doing maps of the sky found a class of objects. They weren't sure exactly what they were at first, but often they appeared to be doubles, as if they came in pairs. Not always. Some of them were single. And in the 50s, they found that those were associated with galaxies as well, but they didn't really know how they related to Seifert's galaxies, so that they were basically just called radio galaxies.
A radio galaxy is a galaxy that not only emits visible light like that you see with your eyes, but it also emits radio waves.
At low-energy radio wavelengths, radio galaxies look very different than how they appear in visible light. What astronomers see in these different wavelengths helps them understand not only the physical processes in these galaxies, but also what's going on in different regions of these galaxies.
At the longest wavelengths, the lowest energies, radio waves, they typically don't see what we normally think of in galaxy pictures. They don't see the starlight, and they don't see a lot of what we normally associate with pictures of the Milky Way or the Andromeda Galaxy. What they see instead typically are these big radial lobes that are outside the boundaries of these galaxies.
Sometimes by themselves, but more often in pairs, these lobes were found to be associated with galaxies containing active galactic nuclei. Galaxies with this property are often referred to as double-lobed radio sources.
And the way that they're formed is that particles get accelerated to very close to the speed of light, 99% or 99.99% of the speed of light. And they get shot out typically in two beams on either side of the galaxy. And eventually these beams kind of fall apart, or they hit something well outside the galaxy, and then they form these big diffuse lobes of radio energy.
But what was accelerating the particles to almost the speed of light? Were these radio galaxies related in any way to Seifert galaxies? The mystery would grow in the 1960s when even more puzzling objects were discovered. In 1960, two astronomers discovered a strong radio source in the constellation of Virgo. They compared the position of their source to objects in a map of the sky at visible wavelengths and only found a faint blue star. When a spectrum of this object was taken, there were emission lines, but at wavelengths where no lines had ever been seen before. The object didn't appear to be either a star or a normal galaxy. The breakthrough came when Dutch astronomer Martin Schmidt realized the lines were normal hydrogen lines, but hugely redshifted. Soon, more objects like this were found, and astronomers dubbed them quasars, for quasi-stellar radio sources.
Quasars were noticed as objects that appeared to be stars, but their light spectra showed enormous redshifts, so we knew they were not within our own galaxy.
These redshifts indicated that quasars were tremendously far away, which, coupled with their apparent brightness, meant that they were incredibly luminous, far more powerful than a normal galaxy. This stunned astronomers.
Maybe the redshift is wrong, maybe it's in our galaxy, maybe it's not. Well, eventually, people came to pretty much agree that all these objects are outside our own galaxy, very, very far away. The redshifts that we see are truly cosmological, truly large distances.
The next clue was found when astronomers studied how quasar light changed over time. They found that quasars display rapid fluctuations in their luminosity, sometimes changing by in just a few days. This indicates that the source of a quasar's energy is not more than a few light days across. incredibly tiny compared to the size of a galaxy. But what could drive the release of energy tens to thousands greater than a normal galaxy while occupying a volume of space smaller than our solar system? Astronomers found that the only object capable of generating that much energy is a black hole. It is possible for black holes to generate light, and lots of it. But that light doesn't come from the black hole itself, it comes from the material falling into it. But the sheer amount of energy emitted from quasars implies that the black holes powering them must be incredibly big, incredibly massive, billions of times the sun's mass.
That somehow when a galaxy formed, material was accumulated in great amounts, high densities, in the centers of galaxies. And the material is gravitationally bound, kept accreting until you wind up having so much gravity in one place that the gravity actually overcomes the ability of light to escape. Then you get a black hole. Well, there's no really upper limit to how much material you can keep accreting in there. So what we're talking about is something that is maybe hundreds of thousands to 1 million or more times the mass of the sun, all located at the very center of a galaxy and taking up space that is of the order of solar systems in size.
Black hole itself doesn't actually produce that much energy, but it's the gravitational pull of the black hole that is converted into energy that we can see. And how it does this is that the gas and dust surrounding the black hole
coming down, caught in that gravitational field, orbiting and gradually spiraling in toward where that supermassive black hole is, the material is just atoms, and these atoms start colliding and crashing into each other because they're being put down into, they're funneling down into this high density region. And atoms are just whacking each other every place, and as they whack each other, they knock their electrons off, they strip their electrons off. Occasionally an electron will find another atom and recombine with it, and it lets off electromagnetic radiation.
And that's what's shining. It's actually the environment of the supermassive black hole. Now, there are several parts to the environment. The very inner part, what's you'll usually hear referred to as the accretion disk, that's the material that's directly falling into the black hole. And that's very deep in the gravity and has a lot of interesting general relativistic effects. But one thing that it does apparently is it, in some cases, shoots out from its poles highly energetic particles. These are what emit the gamma ray radiation, they emit the radio radiation, and some of the X-ray radiation from these jets. And they're those jets of particles provide the big giant radio lobes seen in a lot of quasars. The optical light comes from farther out in what might be kind of a thicker disk that's feeding the accretion disk, but is, in a sense, kind of more normal physics. There's not a lot of general relativity going on out in those sections. And it's lower energy because it's not as deep into the gravity of the black hole. Even further out are probably regions that produce the infrared where there's a lot of dust. These can be out into what we would consider the inner portions of the galaxy disk itself. They have a lot of dust because it hasn't been destroyed by the harsher environments inside and closer to the supermassive black hole.
So each different type of active galaxy is thought to be powered by a supermassive yet extremely compact black hole. But why then do they all appear to look so different from one another?
Astronomers were pretty baffled. They were totally bewildered by just the gross number of active galaxies and how all different they were. And what happens is that in most sciences, the key to understanding different phenomena is to simply observe as many different kinds as you can. You catalog them. You just observe one after the other and look for the characteristics that are similar. The same way a zoologist might look at different types of animals. You know, what does an elephant and a house cat have in common? Well, not much, but when you look at them, you think, well, they both have 4 legs, they're both furry animals, they both have 4 chambered hearts, all of these types of things. You start to get a feel for what a mammal is. You have a unified family of animals that you can classify them in and figure out more about them, these similar characteristics. Well, the same thing happens in astronomy as well. We observe these objects, we observe these active galaxies, and 2 of them may look totally different. But somebody's going to get the right perspective, and in this case, literally the right perspective.
All active galaxies are powered by supermassive black holes, their huge luminosity coming from the accretion disks surrounding the black holes. But the differences seen by astronomers from galaxy to galaxy were due to our viewing angle of those disks.
We don't always see exactly the same viewpoint when we're looking down at the active galactic nuclei. If you can think about it, if you just sort of took a bunch of CDs and threw them up in the air, some of them you'd probably see edge on, and some of them you'd see at an angle like this, and some of them you'd see pretty much face on. Well, the same is true for galaxies. Imagine they're pretty randomly distributed in the universe. And what we didn't realize for a long time is that what we were really looking at was just the same thing at different angles. And so we have Seyfert galaxies. And the way we defined these Seyfert galaxies was by what they looked like in terms of how the radiation was distributed. And what we realized later on is that all these Seyferts are really the same physical mechanism. We're just looking at this gas disk at different angles.
This was the missing piece of the puzzle astronomers had been seeking: viewpoint. When this was taken into account, the different galaxies looked different because of our viewing angle on their central accretion disks. This became known as the unified model. It allowed astronomers to understand the different spectra, both optical and radio, observed from various active galaxies, and the physical processes behind them.
Imagine if you're looking at it straight on like this, it's really hard. You don't see all that matter and radiation that's emitted along the axes very easily because there's this gas and dust blocking your view. Whereas if you're at an angle, you might be able to see a little bit of it coming towards you because you get a little bit less blockage this direction, but you don't see anything behind it. If you're face on, you've got everything coming at you. And so the different Seyferts are really just the same thing where you're looking through different amounts of this disk gas.
We've discussed an accretion disk in the plane of the supermassive black hole. But in the inner parts of that accretion disk, what happens is that something forces particles and energy out the 2 poles, and this is called the double exhaust model. There's 2 oppositely directed jets of material. This material forms the radio jets and eventually the double-lobed radio source when the radio jets decay. It's also where a lot of the high-energy radiation comes from, the gamma rays and the X-rays.
Understanding what drives active galaxies and the angles of observation clarified for astronomers why they sometimes detected only 1 jet in some radio galaxies and 2 in others.
Now, the double exhaust model, because the particles that form the jets are highly relativistic, going very close to the speed of light, there's an interesting general relativistic effect. If you're viewing the object from the side, so that the double exhaust is coming out to either side, you basically don't see the jets at all. You just see the double lobes. The reason is that the relativistic particles emit their light along the direction of the jet, so they're not emitting light towards you. Now, as you change your point of view towards looking more down the jet, you start to see the jet that is pointed towards you because that's where it is radiating its energy along the direction of motion of the jet. But the one on the opposite side is even fainter than it was before because it's sending its radiation away from you. So you're even less likely to see that. Now, it turns out that a lot of single-sided, single-jet radio galaxies were known in the early days, and one of the challenges was to try to see the counterjet. And they integrated for longer into exposures in the radio, and eventually they started seeing these counterjets.
The unified model was pretty successful at identifying the different kinds of active galaxies, but it was also supported by observations of yet another type of AGN, one that produces super high energy gamma rays. The first such object was mistaken for a star. Named BL-LAC, it was similar to a quasar, but when satellites were launched that could detect gamma rays, the highest energy form of light, BL-LAC was found to be pouring them out. Since then, only 40 active galaxies have been found that produce gamma rays, and they are now called blazars. The unified model explains blazars as well. In this model, a blazar is an AGN with an accretion disk seen face-on. Our view of the central supermassive black hole is unobstructed by any gas or dust, and we see the raw power of the jets aimed right at us. If the disk is tipped even a small bit, the gamma rays are aimed away from us, and we don't see them. This not only explains why we see blazars, but why we don't see very many as well. The unified model goes a long way toward our understanding active galaxies. The single phenomenon of a supermassive black hole can explain the many properties of Seyferts, quasars, blazars, and radio galaxies. But there are still many more questions for astronomers to ponder. And perhaps, most interesting of all, why do we seem to see more active galaxies in the past? Although some active galaxies are nearby, we see many more at a great distance, indicating there were more AGN in the past when the universe was younger and fewer today. Why should this be?
Because we don't tend to see these extremely bright active nuclei today, which it would indicate there's been some sort of evolution. There's been a change in how these things work over time. We're not getting these enormous quantities of luminosity due to the radiation coming out anymore.
One possible explanation is that galaxy mergers in the early universe could have triggered the creation or the feeding of the supermassive black holes.
We can see them to the earliest regions of cosmic time, and they are good markers for activity in the early universe. In this model where galaxy mergers are the rule, lighting up the black hole is probably indicative of a time when a merger has happened to rearrange the orbits of stars and gas to actually fall into the central black hole, or that it is an accompaniment to the formation of a galaxy's bulge.
Once a supermassive black hole is formed, it never goes away. The Milky Way itself has a supermassive black hole at its heart, but it is apparently quiet at the moment, inactive. This is also true for most nearby galaxies.
There's no gas trickling into them, and we infer their presence from the extraordinarily rapid orbits of stars right near the center. So there's a huge hidden mass that's making the stars move around. Yet when we look back in cosmic time, when the universe was a third of its present age, that was the era of quasars, and luminous quasars were 1,000 times more common in a volume of space than they are today.
But modern instruments and multiple surveys, using both ground and space-based telescopes, are starting to help astronomers understand what happened in the time between the early universe and today.
So we know that we're in a very dynamical universe, and hunting down that population of quasars is very interesting. So now there's a superb X-ray satellite that has seen those objects where optical radiation might be hidden from us, but hard X-rays penetrate through opaque clouds of dust and gas to come to us and make the marker that there is an active black hole in there, even if our old optical survey wouldn't have seen it. There are extremely sensitive radio surveys that show us that some quasars may be completely shrouded from our view and maybe even too faint for these X-rays, but they show up in distant radio waves. So combining the results of surveys that show us X-ray, radio, and optical is probably going to be the best way to get the whole census of this population, and then understand the era in which galaxies were formed, the quasars lit up, and then they slowly faded away with time.
One of the controversial topics in radio galaxy research is the evolution of radio galaxies. And the idea is that radio galaxies came from quasars. So one idea, which is called the orientation hypothesis, is that they're the exact same object. The second idea is that actually radio galaxies are quasars that have dimmed down or have lost some of their energy. This could be due to a diminishing of the available gas and dust for the black hole to feed off of. In reality, I think it's got to be a combination of both. You know, it's known that there are quasars, and so if you look at a quasar like this, or if you look at a quasar like this, it's obviously going to look different. So I think the orientation hypothesis has to play a role, and I think it also makes sense that, yes, these bright quasars aren't going to have an unlimited amount of fuel supply, and they're not going to be bright forever, so that they are going to dim down, and I think it's actually, the truth is actually a combination of both.
There is an old parable of the blindfolded men and the elephant. One holds the trunk and says it's a snake. Another holds the tail and is convinced it is a rope. And yet another touches a leg and believes it's a tree. They have pieces of the puzzle, but without all the pieces, they are unaware of the elephant standing in front of them. Astronomers see different kinds of active galaxies scattered throughout the sky: quasars, blazars, radio galaxies, and Seyferts. It was only when they put those observations together with a unifying theory that they could see the cosmic elephant, the supermassive black holes that power these active galactic nuclei.